Hello everyone, I'm Zhang Tianqi, a PhD student from Huazhong University of Science and Technology. It is my great honor to present our work named AetEC, Adaptive Error-Tolerant Erosion Coding Scheme with from small mobile devices to large-scale storage servers. Flash memory-based SSDs have become a mainstream storage device thanks to flash memory's small size, energy efficiency, low latency, and massive parallelism. The popularity of SSDs is fueled by the continuing drop in cost per GB, which in turn is achieved by storing multiple bits in a memory cell, and vertically stacking memory layers. Unfortunately, capacity growth is accompanied. There exist multi-level reliability problems of flash memory, which includes bit errors, page level errors, bad blocks, and bad chips. And there exists imbalance of bit errors between weird blocks. Raw bit error rate (RBER) of net flash memory increases with the increase of program and erase cycle. However, existing intra-SSD reliability techniques do not consider both the multi-level reliability problem of flash memory and the imbalance of wear between blocks. ECC can only correct bit errors within a flash page, and RAID can tolerate the multi-level errors, but the number of RAID tolerance errors is limited, such as RAID 5 and RAID 6 only tolerate 1 and 2 errors respectively. For low wear blocks which the error rate is low, the redundancy provided by RAID is excessive, and at the end of SSD's life, RAID cannot tolerate multiple errors in one stream. So there are three key questions at how to ensure multi-level reliability of flash memory, how to ensure the reliability with the best fault tolerance according to the different bit error rates between flash blocks of different wear, and how to reduce the impact of reliability techniques on SSDs. The contributions of AetEC is AetEC applies RS Erasure codes to provide adaptive fault tolerance for the flash blocks of different error rates, and AetEC use FPGA-based multi-rate RS code encoder and decoder to improve. The key idea of AetEC is that AetEC adaptive applies RS Erasure codes with corresponding error correction capabilities according to the number of high wear blocks. To solve the multi-level reliability problem, AetEC adapts various RS Erasure codes to ensure different reliability. To cover imbalance of bit errors between physical blocks, AetEC configures RS codes with corresponding fault tolerance according to the number of high wear blocks in the superblock. To reduce the impact of reliability enhancement techniques on SSD's performance, AetEC adapts FPGA-based multi-rate RS code encoder and decoder to reduce. This is the architecture of AetEC. AetEC adopts a stripe organization method based on physical address and regards a superpage as a stripe. AetEC selects 4-type RS code to ensure different reliability with different redundancy radius. When there is no high wear block in the superblock, AetEC adopts RS-15.1. When the wear of block increases, AetEC will adjust the RS Erasure code to avoid data loss according to the number of high wear blocks. For the high wear chips, the failure tolerance of Erasure code is set to the maximum to tolerate chip failure. We utilize Xilinx HLS development tools to implement FPGA-based encoder and decoder to reduce latency. This is the architecture of our encoder and decoder. This is the resource overhead of our encoder and decoder. And this table is the latency of the processing of encoding and to further reduce latency, we also propose double-linked list red cache. The red cache data includes user data, verification data, and recovered data. At first, AetEC swaps data from the data buffer area to the data parity buffer area. Then, AetEC used the IC encoder to generate the check page. At last, AetEC writes the data page and the check page to the flash in a super page gradually. To evaluate AetEC, we simulated a SSD with a capacity of 64 GB and 20% reserved space with SSD for testing. The parameters of NAND flash chip used in the test are for micro MLC chip. We evaluate based on these indicators: UPER, average response time, average recovery time, and erasure flash times. And we use this table's workloads to evaluate. We test the UEPR of rate 0, rate 4, BART, and AetEC. When the PE cycles is greater than 3.5 thousand, the UPER of AetEC is 2 orders of magnitude lower than that of VAR, a state-of-art near-aware read scheme. It is because AetEC can tolerate multiple chip errors. However, VAR can only tolerate single errors. We also evaluated the average response time. When the PE cycle is 2,000, 3.5 thousand, and 5,000, the average response time of AetEC is 32.8%, 27.1%, and 9.1% lower than rate 4, and the average response time is 1.1% lower, 1.8% higher, and 4.2% higher than VAR. Although AetEC sacrifices some performance that compared with VAR, it provides a high reliability to tolerate multiple chip errors. When the PE cycle is 2,000, 3.5 thousand, and 5,000, AetEC reduces erase time for 38.8%, 25.9%, and 2.4% compared with rate 4. For chip error, the offline recovery time of rate 4 and AetEC is 19.12 seconds and 19.78 seconds respectively. For die error, the offline recovery time of rate 4 and AetEC is 18.84 seconds and 17.16 seconds. When die error occurs, AetEC makes full use of SSD's parallelism, so the recovery time is less than rate 4. More in the paper, reliability modeling and analysis of AetEC, and the double-linked list red cache to reduce latency, and the implement details.